Welcome to Wireless Future, episode 49, and I'm Emil Björnsson, and as usual I'm here with Eric Larsson. How are you?
Hi Emil, good, how are you?
I'm great. So, what should we talk about today? Have you been traveling anything lately?
Oh, indeed, I have, and I attended a few events recently, and in fact one that I would like to tell you about, Emil, is the 6G workshop organized by the New York University in Brooklyn, New York, that I attended last month.
All right.
Yeah, have you ever been there?
No, actually not. I've been invited a couple of times, but I'm trying to keep down my traveling a bit, and unfortunately haven't fitted my schedule. But it looks every time like a very interesting event. I think during the pandemic, I actually joined online a few times.
Yeah, but this time it was in real life, and it was the first time. But I mean, totally, I agree. I also try to keep down the travel, but then it's of course difficult to resist when you get an invitation to speak at an event like that. And it was a really great conference. I think, in fact, it was something like a role model for how a scientific conference should be run and organized and executed.
And NYU, that is like New York University in Brooklyn, or?
That's right, in Brooklyn. So they've got this research center for wireless, NYU Wireless, that organized the workshop. And this year the theme was on 20 years of massive MIMO. What's next?
Wow, 20 years. So it really has been some time.
Well, you can always debate, of course, when was the real birthday of massive MIMO, but what I think is less open to debate is the enormous impact that this technology has had. And so that was like the leading theme of the event, and there were like 3 main sessions, and each session consisted of a lineup of invited speakers, and then there was a short break with coffee. And after the break, there was a, let's say, a free speech open mic session for about an hour, where anybody in the audience could ask questions to the speaker, or ask general open questions, or make statements. And also the chair of the session had some questions for the speakers, but more interestingly, also for the audience. So the chair of the session might cast an open question and then point to somebody in the audience. For example, Emil, could you opine on this question or this issue? And then you were expected to grab the mic and stand up or walk up front and deliver your viewpoints or counterpoints, which I think is exactly the way that science should evolve and that this sort of events should be run. So that was a lot of fun.
Yeah, I think this is definitely a type of event that is really important for our research community, particularly when these big conferences have been growing to such a large extent that, you can't really fit everyone in one place, and no one really have time to listen to any paper presentations. So having these really discussions which gives you some value that you can't get from just reading people's papers, that sounds like really what we're after in our community.
Yeah, that's what we're after, and what we are to some degree, I think, missing. I mean, some of the big conferences might be better than others in terms of actually offering this kind of discussion fora, but by large, I think we could do a lot better.
Yeah, and I think the setup that there actually are discussions, and that is important part of it. I think that's really good organized, because I think often panel discussion at big conferences is like, okay, you have 1.5 hours and everyone gives an intro speech for 10 minutes, which turns into 15 minutes, and then there is like 30 minutes of discussions and only predefined questions, so then it doesn't really turn into what you described here. So I feel that I should have been there. So what did you really talk about, or was there, for example, anything new related to MIMO there?
I mean, there was definitely a lot of discussion about MIMO, and also I gave a talk that touched upon some aspects of MIMO. And one thing where I started off was that there is quite a bit of talking in the community, and especially among operators, that massive MIMO doesn't really deliver. And then the question is this true to start with? And if it is true, then what are the root causes of this observation? And in fact, it seems that a lot of times we just got a single user in the cell. And obviously, if you only got a single user in the cell, then massive MIMO isn't of much utility, because the entire idea behind massive MIMO is the spatial multiplexing capability, where you can serve, in the textbooks, I think we had something like 30 users at the same time with 100 antennas. Maybe in practice you can't get 30, but you could at least get 10 or maybe 20 or something. So that was one talking point.
Right, and when it comes to that topic, to my understanding, that is true, but it's not exactly like that. My impression is that we have expanded the bandwidth of the system by 5 times or so compared to 4G systems.
Yeah.
And there might be many users in the cell, multiple ones, but it is enough to just give them different chunks of the spectrum.
Yeah.
And so on every subcarrier there, it's roughly one user, but not...
That's right, and that's such an important point. And in fact, this was also a discussion point raised by the audience, that, maybe is it that the operators just have gotten too much spectrum, so that we aren't really, air quotes, forced or encouraged to implement and make use of spatial multiplexing capabilities, but we're interlocked in this thinking of chopping the frequency and multiplexing with FDMA and so forth. It's possible. It really seems that if we can afford not to use the spatial multiplexing capabilities of massive MIMO, maybe spectrum has just gotten too cheap, or there is too much of it in relation to the bandwidth. In relation to the data transmission requirements that we've gotten. The other point, I think, is that a lot of the higher layer protocols are just very poorly designed, in that they aren't constructed to make good use of what massive MIMO can offer at the physical layer. Because in fact, a lot of the bits that are transmitted in the network come from services that are fundamentally streaming at maybe not completely at the fixed rate, but at least streaming. And there's just no reason why those sources of data should be chopped up into small packets that get scheduled in the time frequency domain and so on. No, they should just be sent. Everybody should get the wire in the air that's offered by the massive MIMO spatial multiplexing, and then as little retransmission protocols as possible, as long packets as possible, coding over as large time frequency bandwidth as possible, which is something that seems to be just misdesigned in the standards. And my understanding is that this is all because of legacy, because we have this TCP/IP underlying protocol stack and so forth, and we got a HARC process on the application layer, we got HARC process on the access layers, and then we got another HARC process. This is completely, I think we're completely in need of a redesign of not only the physical layer, but the entire protocol stack for high volume streaming data, where massive MIMO really will shine. So that was like one of the points that I also try to convey in my talk. And related to that, go ahead.
Yeah, and I think people have for a long period of time talked about cross-layer optimization, as that it's important to optimize things across the different layers of the protocol stack. But I'm not sure how much of and maybe some of those things have been happening at the lower layers. You have optimized the resource allocation and the physical transmissions. But I think people who are actually building the applications, they just try to do something that they think is good for their users in terms of that if you are scrolling through Instagram, then they want the videos to show just a few seconds automatically directly, so it downloads those things, and they do something there that they think are optimized for their application and the user experience, but it might not be good for the network as a whole.
Well, I mean, it doesn't make use of what the physical layer and what Massive MIMO has to offer, right? So that's the point. And I mean, just as you said, cross-layer optimization has been trendy for at least 20 years, and so basically we know how to do these things. It's there, it's in the papers, in the textbooks, but it isn't implemented. And as a further consequence of all this chopping of, I mean, you got data packets that are fundamentally large, entire chunks of videos that you're gonna stream, and you chop them into short packets that you schedule in the time frequency domain back and forth and so on, and you don't make use of spatial multiplexing. So an additional consequence of that is that the signal to interference and noise ratio, when you look at the OFDM time frequency grid, becomes very random and fluctuates up and down, which makes link adaptation extremely difficult, if not impossible, because the whole idea with link adaptation in Massive MIMO is that you should schedule users for long enough so that you get a stable, effective SINR that you can easily measure, like reasonably accurately measure, and then select an MCS, I mean, modulation and coding scheme appropriate for that. So that's another one, So here we could go on about this, I guess, and we are not, I suppose, but...
No, but I think this also somehow, really reinforced the point that sometimes people do something to make it simple, but then it turns out that they have large-scale consequences. So I think when people have been designing sort of the scheduler for the systems, they say we would like them to have as much mandate to do whatever decisions they want. So you shouldn't expect that just because I give you some time frequency resource right now, you will get the adjacent ones in time or frequency in the next round. So therefore you don't really know how your channel will evolve, and in the same way, even if you happen to know who will be scheduled and what interference that will cause in the neighboring cell right now, you have no idea what will happen in the future, and this makes the whole scheduling much easier because there is no dependencies. You don't need to care about anything, but of course you get the problem that you described, and later on when you try to guess what performance you can deliver right now because you have no idea about your interference.
Exactly. I mean, you wanna take out as much as possible of the randomness, right? So that you can predict what is the SINR I'm actually going to have over this time frequency block, and so you can adapt your transmission beforehand.
But it sounds what you are advocating for is a little bit how things were done maybe prior to 3G, where you have this kind of circuit switch things where you created, in that case over frequency, you created like, here are the subcarrier delivered to this mobile phone so you can make a call, and here is one for another user. Would you like to have something similar? Then you have a beam, and then you keep that beam and those frequencies even if you don't have any data to transfer.
I mean, let's face it, a lot of data is more suitable for packet-based transmission. There's no question. But it's also true that the vast majority of the bits sent over the network actually come from sources that are fundamentally circuit switched or streaming, like video transmission, I think is a good example. Anyways, and another point with Massive MIMO that's sometimes raised is that it doesn't work well at the cell edge because with reciprocity-based beamforming in TDD, which as we know is the way to implement Massive MIMO, then the mobiles don't have enough transmit power such that the received pilots are too weak, so reciprocity-based beamforming doesn't work. And I think that's a legitimate concern. I mean, it's more than a concern, it's just a fact of physics that if you have a limited power and you spread it over a very wide bandwidth, then the SNR per dimension goes down, and at some point the reciprocity-based channel estimation will stop working. But to me, the root cause here really seems to be that, maybe we are spreading over too large bandwidth.
Yeah, we're coming back to that the operators might have too much spectrum, because I think what typically happens is that the mobile phones, it has a particular transmit power it is allowed to use, say 100, 200 milliwatt, and there are safety reasons and battery reasons why you shouldn't go beyond that, while the base stations, their power typically can grow with a much large amount of spectrum that they're having. So
That's
they
right.
have been growing while you haven't grown in the same way on the mobile phone, and it creates these issues.
That's right. The uplink downlink imbalance probably has increased even, and it's a fact of physics that if you spread your fixed power over more and more bandwidth, the SNR per degree of freedom decreases. So the only way is to use less bandwidth and more aggressive spatial multiplexing instead.
Right. And then, of course, one could then say that what they have been doing now is to say, if the amount of traffic that people are having is not high enough, so you can give them different chunks of subcarriers instead and just divide up like that. Well, then they focus their power on those subcarriers, spread it out over time, and in a way that is a reasonable response to that problem, even if it means that we are not really utilizing the spatial multiplexing.
That's right, because then effectively, I mean, you're singling out parts of the spectrum where you spend your power, and then you regain your SNR per degree of freedom, so that reciprocity-based channel estimation works again.
Right, but I think that also then the fact that when you deploy a new network, and if it has, say, 5 times the amount of spectrum, and then hopefully some 4 or 8 times more capabilities in terms of spatial multiplexing than in the past, then it's not like you immediately will have more traffic that was just waiting to happen. So it sort of makes good sense that the traffic will grow up over time, and then maybe eventually we will need these capabilities more and more, and then we will really see when the network gets stress tests if they actually work well in terms of spatial multiplexing. And I think what you heard was this kind of feeling that in the cells where the traffic has grown so much already, the implementations doesn't really work as well as theory is predicting.
I think that's what it seems like. Right. So then, I mean, related to this, there was actually both in my own talk, but also in some of the other presentations and in the discussion, there was a lot of talking about channel state information, which kind of warmed my heart because, as we know, I think it was actually Tom Marcetto who coined this phrase like 10, 15 years ago now, that channel state information isn't everything. It's the only thing. And this has always been true, and it remains true more so than ever. And it's really about getting the CSI for beamforming. Of course, an uplink, that's not an issue because in principle you can decode blindly. But on downlink, you need to know where and how to beam your power. And we should keep in mind that there are a lot of different sources of errors in the channel state information or in the channel estimates, right? I mean, there is noise obviously on the pilots. There is contamination on the pilots from the sheer fact that pilot sequences are used in other cells and so on. There is channel aging because we estimate a channel and then the mobiles, the terminals move around and the estimates get outdated, so we have to re-estimate. And also in cell-free or a distributed MIMO, there might be phase errors between the different antenna panels, depending on how they are phase aligned. I mean, do they have like a common reference clock that they distill their phase reference from, or do they have free-running oscillators that have to be periodically aligned and so on? And the accuracy of this channel state information is really a limiting factor, which is a point that I took the opportunity to one more time drive home, but there were also other talks. There was one, for example, by Jilin from China Mobile, who also reinforced this exact conclusion. And especially in cell-free and DMIMO, this is the number one technical problem we've got to solve in order to make these systems work. And then I also had some interesting offline discussions about channel state information because, even with point-to-point MIMO, of course, channel state information is crucial, right? I mean, you got an antenna array, and you got the receiver, and you want to achieve capacities, and then we know the optimal thing to do is the singular value decomposition, and to do that you need channel estimates. And I also had some discussions with some folks about OAM, which is a particular instance or form of point-to-point MIMO. And I think an important takeaway here is that channel state information is as important for point-to-point MIMO, for OAM, and so on. And in some cases, channel state information just means that you know how to point your antenna, right? I mean, it's important even for the dish antenna. So it's important for a fully digital MIMO array. It's important for an OAM. It's important for a dish antenna. And for the dish antenna and the OAM, it might just mean that you need to know how to precisely point your transmitter, which is you got to know the azimuth, the elevation, angles, and so on. That is what channel state information mean in that. Yeah. And this can't be said enough many times, I think, because yeah.
No, and that also connects to some of the topics we talked about in recent episodes. So when we talked about sensing systems, for example, those that are systems that are used by the militaries to really do sensing, they can actually physically move around, at least horizontally, and point beams or point their directivity in that way. And we talk, I think, in the last episodes about movable antennas as one topic, and I think one particular instance of that people are researching is rotatable antennas. You would have some base station that can actually rotate in different ways and can optimize. And then, of course, you need an even deeper kind of channel state information for that to happen.
Yeah, that's right. I mean...
And I think engineers they in 3GPP, so they are doing their best to do something out of this. And I don't know exactly how well things are actually working in practical systems, if we are limited by fundamental problems or if it's just implementation challenges. But I read up on all the things that they have been trying to do in terms of channel state information feedback, because the alternative way of this reciprocity method that you are describing is that you transmit in a downlink where you have more power, you transmit a number of different signals, you measure the channel, and you defeat it back. And then the challenge instead becomes, how do you describe your channel in a confined way so you can feed it back over this low capacity uplink link that you're having before you know the channel. And they have been doing all kinds of things like determining how frequently in time should you sound your channel and estimate things, how frequently in frequency domain depending on the frequency variations, and what kind of can you divide up things in spatial domains? So you say, I know this link will only be described by 5 main directions to represent the different physical objects. So there are all of those type of things there in the standard that you can implement. But I don't think it has been implemented, because I think just the basic features there of feeding back a vector occasional to describe the directions, that consumes a lot of uplink feedback as well. So you can do it, but it's always a research question. You can also send a lot of uplink pilots in order to build up SNR, but it would eat up such a big fraction of your resources that it's not worth it.
That's right. But I mean, that's an important point. Of course, rather than a reciprocity-based beamforming, you could send this feedback, and then I guess machine learning would come to the rescue, right? I mean, fundamentally, measuring the CSI now at the mobiles and then compressing it is a data compression problem, which we know AI is excellent at. So using some kind of neural network to do this, it seems to be the way to go. My point is rather that nature and physics gave us reciprocity for free, so why not exploit it? I mean, could even be combined with feedback, right? So yeah, anyway, maybe we should not digress.
So you mean now that reciprocity isn't everything, is the only thing?
It might not be the only thing, it's something that's out there that nature gave us for free, and we know it's a very juicy and good thing. It's a very useful thing, so we should exploit it. I think that's yeah. And for those who also wonder, where does this kind of quote come from, there's actually an American football coach who once said, winning isn't everything, it's the only thing. So it's somehow, the only thing, yes. And I think there are many versions of this ones, if you Google around, that people have been adapting this for different topic. Yeah, wow. So what else did people talk about? Anything sensing related? Yeah, I mean, of course, sensing, because it seems like it'll become an important aspect of 6G with integrated sensing and communications. And one point there, I think that also I made is that wireless sensing integrates very naturally together with dynamic duplex in MIMO.
So what is dynamic duplex now again?
So dynamic duplex is when you shift the switching point, so that normally everybody switches from uplink to downlink at the very same instant in time. But with dynamic duplex, then you shift so that not everybody switches from uplink to downlink at the same time. So you create like some part of the slot where access points or base stations actually can send to each other, and you can serve uplink and downlink users simultaneously. And there are some capacity advantages, or some advantages in terms of capacity of doing this if you have a lot of imbalance between uplink and downlink traffic, for example.
Would this be another source of this kind of interference that we talked about before, that is unbalanced?
Totally, there will be interference. I mean, in dynamic duplex, there is interference between users and between access points and so on. But actually, it is this interference between access points that could be exploited for sensing, right? Because you would then create a part of the slot where one access point transmits, another one receives, and that's exactly what you want in a bistatic sensing setup. So,
yeah, no, I've been thinking about a simple version of these type of things myself. That the natural thing in such a distributed MIMO setup would be that when you're transmitting in the downlink from your base stations, a few of them are turning themselves into uplink mode and just listen instead. And of course, you can do this even more dynamically by switching in different ways as well.
Totally. I mean, that's I think, again, dynamic duplexing comes very naturally together. It goes hand in hand with wireless sensing. So that was one thing. Yeah, I think looking at the future, it's very likely that a lot of data in future networks will come from AI-related applications. The argument that I've been making is that AI has gotten extremely impressive. I mean, it's basically read the entire internet, and everything that any human has, written or spoken, or every blog out there, every show on YouTube, every podcast, every scientific paper probably. So the only way for AI fundamentally to get any better will be that we feed it with more data. And there is only so much data that humans can generate. So all this data is more likely to come from sensors of various kinds. I mean, it could be cameras, obviously, it could be radio, could be RF, could be anything. But bottom line, very likely this data, it's got to be transmitted somehow. And a lot of that transmission is going to happen over wireless. So I think if this AI revolution is to continue, then it will necessitate high capacity wireless networks that can deal with all the information. And then we should keep in mind that a lot of this data, I mean, raw sensor data for one thing, but also, when you train machine learning models and you send updates and use gradient descent and you send these gradient models and so on, this kind of data is fundamentally different from sending like the kind of bits that we are used to transmitting. So that in turn might very well entail also a redesign of the entire protocol stack from the physical layer and up. And one specific technique that I find a bit fascinating is this over-the-air data aggregation, where you basically rely on superposition principle of the wave equation to, everybody sends like data and it kind of adds up in the air. So you're interested not in the individual streams, but only in the sum. And interestingly, I mean, if you want to make that work with coherent superposition, then we are back at these channel state information and phase drift and phase noise issues that we mentioned earlier. So also there, it seems that channel state information is going to become one of the limiting factors. So this punchline on channel state information that we talked earlier, remains also pertinent there. So that was one point. Yeah.
Yeah, and if I understand this correctly, it's like you have some data that you have collected and you want to transfer to other place, and if what you will do as soon as you get that data as input to an AI training or so, is that you will just combine the data in a particular way.
Yeah.
Then it's unnecessary to send them as parallel interfering streams over there and then combine them at the receiver. You want to do it over there.
That's right. If you're only interested in the, let's say, arithmetic sum of the data, right, which is the case in some of these machine learning applications where you train models using decentralized data and so on.
Right, but then you also come back to this situation where you, in order to do that, you want the different streams to be, having similar sync-to-noise ratios, so that they are adding up, not only in phase but also with a similar strength. And I think that would be a challenge in practice.
Yeah, it is it's a major challenge, Emil. I mean, you're right. I mean, not only you want the phase to align. But you also need to scale the amplitudes. Essentially, you got to invert the channel rate for this to happen, in its most basic form, at least. So that's like one general topic that was also discussed a bit, and that I talked in my own presentation.
But do you think there is anything one can do when it comes to over-the-air computation which doesn't require this phase synchronization? I mean, at the end of the day, you want to transmit something, you want at the other side to compute an estimate of maybe the sum or something.
That's right.
And you can perhaps extract something anyway without phase synchronization, or what do you think?
One can, yeah. I mean, there are non-coherent versions of it where you basically send everybody sends a sequence weighed by an amplitude, and the receiver estimates the power, which you get very noisy measurements, but it still works to some degree in some applications, especially when you feed these estimates to like as gradient updates to a machine learning algorithm. They tend to work fairly well because those algorithms are so resilient to noise. It's pretty much enough that, whatever you receive on average has the right sign. So the expected value is positive, and then okay, it's horribly noisy, but so what? It still works. So yeah, maybe we shouldn't go there today. I mean, but that's a whole very technical topic, which is quite interesting in itself. So yeah.
All right. So did anything else you picked up from these sessions?
I mean, there were a lot of other interesting. So now we talked a lot about points that I brought, and there were a lot of other interesting talks as well. For example, there was one by my colleague Sara Wilhammar, who spoke about fading models, and especially about the IID Rayleigh fading that I think you and me have debated in the past quite a bit. And the punchline here was that it's a very rare species. I mean, you have to look very hard to find it, but he actually did find it in some measurements where they were in like an indoor environment with really a lot of scattering, a lot of metal that really creates this kind of isotropic environment where you get almost IID fading, which is kind of neat. I mean, because a lot of times, as we know, you have more like correlated fading, and you have line of sight paths that can be quite strong and so on. And also in the same talk, there was the point being made that, well, now if we don't have IID Rayleigh fading, maybe we can create it somehow. And how would we do that? I mean, one way is this concept of swarm repeaters, to deploy network-controlled repeaters, calibrate and configure them so that they are reciprocal, and deploy them in large numbers, so that they basically, each one of them acts as a scattering point in the channel, but with significant amplification. And didn't we talk about that, Emil, the other month on the podcast? I think we did, right?
Maybe at least we have talked about swarm repeaters. Maybe it wasn't in the, last year, but when you describe this from the perspective of wanting to create IID fading, is the goal then to have like a point-to-point link with multiple antennas on both sides and give you a good channel condition there, so you can send multiple data streams between two places?
I mean, I think it's more generally of course, you can never create IID fading, but you can at least enhance the richness of the channel, right? So basically you can, of course, improve coverage. If you got like coverage holes or you're blocking, poor SNR because of blocking, but as importantly, I mean, you could create additional propagation paths that increase the rank of the channel, which would be mostly important, as you said, for point-to-point, or when you have very closely separated receivers, so that you start with a channel that has low rank, and now you add additional paths to it to increase its rank.
Yeah, no, I was asking that question because I think when people have been working with theory, I think there's a good understanding and even mathematical proof of that. If you want to have a high capacity for a given SNR or a point-to-point link, you want to have something IID-like, so you get the many different paths. But then when you do multi-user transmissions, then each individual link doesn't necessarily need to have IID fading. If people are physically separated, involve different set of scattering objects, it might even be better because they become more isolated from each other.
Yeah, I mean, that's a good point. We got to be careful to distinguish multi-user MIMO from point-to-point MIMO here. And one thing we know is that multi-user MIMO, if you get single antenna terminals, works pretty much as well in line of sight as it works in IID Rayleigh fading. So then there wouldn't be a lot of point in enhancing the rank of the channel. But when you got multi-antenna terminals, then effectively you create a point-to-point MIMO channel to each one, and then it still pays off to increase the rank.
Yeah.
So I think by large, I mean, scattering is a good thing, and especially when you can introduce scattering that has significant amplification of the paths, which is precisely the point of this swarm repeater concept.
Yeah, and I mean, if you're serving two uses that are relatively well separated from the beginning, you put a repeater in between them that amplifies the mix of the signals. You can actually degrade the performance unless you do cross-layer optimization, as we talked about before. So it's not necessary that you just throw out hardware there and everything becomes better. Yeah, channel state information and the good design of them is important to really get what you want out of it.
Yeah, no, I agree. I mean, it's reassuring to also hear you saying this, Emil, because it means that there's still a lot of good topics for research and development in wireless comms.
Nice.
In fact, yeah.
So what about frequency bands? Are we stuck below 7 gigahertz?
Yeah, I mean, so there's this endless debate, right? How high should we go up in frequency? And of course, millimeter wave didn't really become such a great success for 5G, as we know, because I think some countries even installed equipment and then decommissioned it because there was not enough need for it. But what we don't know, obviously, is in the future what new applications that will come along and that will really require these enormous data rates that we can offer when we have this at these high frequencies. So in the workshop, there was also a lot of talks and discussion about high frequencies and especially terahertz, which is something where, I mean, I was really in the learning mode here because I don't have much working experience on it, and I found it pretty interesting. And specifically, there were presentations that I found quite interesting about moving as much as possible of the signal processing as close to the antennas as you can. I mean, using low precision 80 converters, obviously, which is, by the way, not a new concept as we know, but still it can become very useful in this context. And there was also a very interesting talk by Daniela Cabridge on using true time delay beamformers at terahertz. So rather than just building a phased array and shifting the phase, you actually implement a small configurable time delay per antenna element, which brings huge benefits when you have wide bandwidths and these large arrays.
Right, yeah, and I think that is also a concept that has been around for 20 plus years, but the question is whether one can now actually build such unit in a power efficient
but I mean, to be fair, I think a lot of the ideas that we are talking about in comms engineering and MIMO and so on, they have roots that go back very far in time, and maybe it is that for the terahertz here now particularly, definitely there will be signal processing challenges that are novel, but above all, it seems to me that these are implementation challenges of actually building the microelectronics and getting that to work. And then maybe in the end, it will be like, here's what is actually feasible to do in terms of constructing the hardware. And that hardware will have certain limitations. And then we've got signal processing problems that comms engineers can come in and attack. For example, given that we have true time delays that have certain capabilities, that you probably will have like a maximum delay, you will have quantization steps and so on. What is the best way of using such an architecture? And I think that are still interesting, partly open problems to tackle. So a pretty interesting topic indeed.
Yeah, no, and I think if we talked earlier about that maybe operators have too much bandwidth and don't need spatial multiplexing, I think if we would build links at terahertz frequencies, we will have immense amount of bandwidth there. So it's mainly about closing the link, pointing the beams towards each other, and overcoming those challenges, not to... But are there any other phenomena that are showing up there that are interesting beyond sort of just pointing beams towards each other and make use of the spectrum?
I mean, there is some talking about the fact that we, in a lot of these systems, will be in the geometric near field of the antenna array. So that beams don't exactly look like in a lot of the textbooks. I mean, you got this like very cartoonish, but that's not what the beams look like. And depending on how you configure your phase shifts or your time delays, you can get beams that take on different shapes. And particularly you can get like beams that look a little bit like curved like this and so on, which is quite nice. But what we should keep in mind here is, and that was also a point made by somebody in the audience. I was about to state this point, but then somebody else made it before me, that, look, the old-fashioned time reversal beamforming, time reversal in the time domain, which is the conjugate beamforming or maximum ratio transmission in frequency domain, is always optimal. You can never do better. So given that you have accurate enough channel state information, which means in this context that, you basically know if you're in like free space line of sight, it kind of just means to know the angle and the distance. If you got blocking objects, you got to know where are these objects and so on. So that you can compute the channel impulse response from your target point to each one of the elements in your array. You can never beat maximum ratio transmission, also known as conjugate beamforming or time reversal beamforming. I think that's important to keep in mind here, which again is something that's been known for decades. I mean, so,
Yeah, and I think sometimes people are just describing this as a collection of different kinds of other beam shapes that are better in other ways. But yeah, I think you're totally right that at the point where you want to focus it, what you describe is the optimal way. It doesn't matter what it should be. No. If you want to create some other beam shapes, you should have other motivation for doing that. You basically say, here is my focal point. I can trade away so that I get a little bit less power there. And what I gain is that I can shape the beam, and that could potentially be useful if you don't really know where your true focal point will be and you want to widen this area somehow.
Yeah, absolutely, Emil, and that's a really interesting and relevant topic, I think, also to work on. That we aren't only interested in maximizing the SNR at the target or focal spot, but we want to make it like as wide as possible. But also there we should keep in mind that there is a huge body of literature on robust beamforming techniques and all sorts of things. Let's not go there today, but I'm sure more could be done, and especially at these high bandwidths and high data rates and also high Dopplers, we need computationally efficient algorithms to do the job. So I think there's ample of opportunity here for comms engineers and signal processing engineers to invent new algorithms.
Right. So if we then leave the wireless common sensing, were there anything about computations or anything about that topic?
Yeah, definitely. I mean, of course, there's a lot of talking about, again, AI, decentralized and federated learning as possible drivers of new networks design for, if not for 6G, maybe for who knows what. I mean, I suppose there'll be a 7G and 8G, and development is not going to stop, right? But it was also a thought-provoking talk that basically asked the question whether the demand for wireless comms is becoming saturated, so that innovation will rather be driven by desire for cost reduction, more so than getting more bits, getting like better coverage and all of that. And I have less intuition for this. I mean, I can somehow sympathize with the sentiment that now we got this technology, which after all works very well, and it's quite cheap for consumers. And if we are to, roll it out in more places in the world, and we are going to improve coverage in like weak spots, then maybe we don't want to pay a lot more, and that means we need to make it more cost efficient. So that was one thing. And there was some talking about spot markets for spectrum among operators. Could we trade spectrum rights on a millisecond level basis? Which is not a new idea. We had a European project on this. That was now, if I remember well, 15 years ago. Sapphire was the name, where the idea was to trade spectrum on a slot basis between operators. And these ideas seem to be coming back periodically, and it's difficult to tell the realism in it because it would entail a lot of regulatory change, presumably. But it's quite interesting to think about. And how would you integrate that with modern MIMO? How would you integrate this with massive MIMO? I mean, that I think is largely an open question. So that was a bit interesting.
Yeah, and I think this also comes down to who is owning the customer that are then paying something for getting this kind of access. Because if we have with regulation try to create that markets by saying that, well, we should have some free 4 different national telecom networks in each country to create some kind of competition. And if you compare this with like the power grid, yeah, we have multiple companies in Sweden that build power plants, and they are building power lines and so on, but they don't cover the same regions. So you don't build 4 different power grids that are on top of each other. So and what people are then doing is that they get a contract from a company that is then buying power from these different places and put together a good portfolio for you and hopefully give you a good price. So potentially the business models for access should be better or different in the future, where you buy connectivity that can come from any network. But of course it would be a very radical change for these companies that you are today having your contract with and owns these physical networks.
Yeah, probably. I mean, and there was actually also a question cast by someone to the audience that, look, we got all these services, right? And as a consumer, say, Emil, that you were to pay another $5 a month for your, cell phone subscription. What service would motivate you to actually, would make you feel that this extra cost is worthwhile, given what we have and how well it works? And somewhat startlingly, nobody in the audience could really deliver a compelling answer to that. So I think here's something to think about. Anyways, so it was altogether a good discussion on some let's say more softer maybe topics that are definitely relevant for any 6G discussion, any beyond current standards discussion.
Yeah, and it's definitely important also from this viewpoint that we can design technology, we can standardize it, but if it's never deployed or very limited areas where the deployments are happening, then is it really going to be important and have an impact in the future? And I think technologies that can bring 6G connectivity out in the countryside and provide good services there. Of course, the capacity doesn't need to be the same because the demand is not the same. But if you can go around anywhere and feel that my service is the same, from my viewpoint, then I think that will have a much bigger impact than maybe squeezing out a few extra bits in the city center where you anyway can just deploy things more densely.
Yeah. Totally.
So finally, then, do you have any other thought-provoking conversations that you would like to share with the audience?
I mean, I had a lot of good conversations on different topics, ranging from like more general aspects of next generation wireless to more specifics. And one conversation that I remember especially vividly is at the lunch table together with Torkel Hansen. He's an expert on electromagnetics, and Ruth Gememberin is a grad student of Thomas Marcetta. We were sitting together and we were talking about, because both Ruth and I raised the point, coincidentally we were sitting on the same question, because a lot of papers make statements about superdirectivity in antenna arrays and about mutual coupling between antennas and so on. And a lot of papers claim that superdirectivity phenomenon is a consequence of mutual coupling, which I could never get my head around. I mean, I felt like, why would it be the case? And I don't understand, what they're saying like this. So I brought this point, and it is very clarifying, because superdirectivity has nothing to do with mutual coupling. And it's such an important thing to understand, that it's something that seems a lot of people has gotten wrong. At least it's wrong in a lot of papers.
Yeah, I could probably have said something like that myself without having studied the topic. Right?
Now, here's the thing, that mutual coupling is a phenomenon that you'll be subjected to in an antenna array, where you got antennas that sit, well, distance doesn't matter, but it's only significant if they're like close to each other, right? So let's say you got two antennas close to each other, and you induce a current in one of them. So you drive one of them with a current, okay? Then that antenna will radiate an electromagnetic field, and that in turn will induce a current in the other antenna. So they will like affect each other. They couple with each other. And to model this properly is not at all trivial. I mean, but the physical phenomenon is called mutual coupling, okay? And then, almost unrelated to that, there is the phenomenon of superdirectivity, okay, which is that with an array of M antennas, let's say in free space line of sight, okay, conventional textbooks in MIMO typically teach that we can achieve an array gain of M. But actually, the array gain that we can achieve is M square. That's a superdirectivity phenomenon. And this can be achieved even if the antennas are point sources. And point sources can't affect each other. I mean, you drive a point source with an ideal current source. It is what it is. It radiates what it does, right?
Right, but if you just superimpose the signal from multiple sources and there are M sources, then it seems like it should scale with M. So where does this M square come from?
Yeah, so now this is getting pretty technical, Emil. I think it would deserve an episode in itself, all right? But it's actually explained in one place where it is well explained is in the book chapter by Tom Marcetta and Torkel Hansen and me. That came out in, let's see, it was a title. It's an edited book that might not have gotten a lot of visibility. I'm actually not sure, but I can send you the chapter. It came out the other year. And so here's the thing, that in order to compute the array gain properly, in this case, what you got to do is, let's say you do it for a scalar field. So it could be like a pressure source, okay? It could be like a liquid or air. So the field here is the air pressure. So that means that a point source means that you inject a tiny amount of air, or you suck out a tiny amount of air at each one of the point sources. And then what you got to do to compute the array gain is that you can definitely sum up, because of superposition principle, the green function, which is like 1 over r e to the jk into r. Any point in space you can sum up from the array. Okay, but then to compute the array gain, what you're gonna do is that you're gonna compute then this amplitude, okay, square it, and then normalize it by the total radiated power. And the total radiated power is what you get if you take this amplitude square, okay, and you integrate it over a sphere that encloses the source array. And that integral is a little bit, you need a few lines of calculation to get it. But then you'll see in the end you get something which, when the separation is large between the sources, the gain is m. But when the sources get closer and closer and closer, the gain approaches m squared. And that is the superdirectivity effect, which has nothing to do with mutual coupling, because there is no mutual coupling between point sources. Now, that said, it's also important to understand that in any practical system, if you were to build an antenna array, then you would have dipoles or patches or, whatever, okay? And if you put these closer, because superdirectivity only can happen if antennas are closer than half a wavelength, yeah? Now, if you put real antennas, like dipoles, closer than half a wavelength, in order to achieve superdirectivity, then mutual coupling will become very significant. So they kind of go hand in hand, but one isn't the consequence of the other. Superdirectivity can be achieved with point sources, and when the sources are close enough together, and in that case mutual coupling becomes a very significant effect. So that was a very good discussion, which confirmed something that I thought, this is what it's got to be like, but a lot of papers claim something else, and we felt it's very strange why they say like that. So,
but let's see if I grasp this correctly. So is it so that you get this m square not necessarily becomes you get an unnaturally strong signal in a particular direction, but just that you radiate much less than you would normally expect, and therefore the ratio
radiated power. Yeah, I mean, in like information theory MIMO books, then the radiated power is the sum of the squared amplitudes of the signal you feed to the array, right? But the physically radiated power can be quite different. When you have half wavelength spacing, they coincide in free space, okay? But when you pack the antennas more closely, then the radiated power becomes something else than the sum of the input amplitude squared. Yeah, I'm going to send you the chapter, Emil. It's quite comprehensive. It's only a couple of pages, actually, to a very lucid derivation. That.
All right, right. That's really nice and very enlightening. And I hope that the audience who stayed all the way to the end of this episode also found this enlightening as well. So thank you very much for sharing your experience from the NYU Summit there on 6G. And
thank you, Emil.
And I hope our audience will come back then for the next episode, which will be number 50.
Wow, number 50.
Yes, so thank you very much for listening, and see you in the next episode.
All right. Thank you, Emil. Bye-bye.